And we'll go from current slide. And I've got a couple of announcements. One of these is new, so I do want to let you know about this. This is lengthy too. I'm going to go on my projector as well. So I'm going to try not. If you know of anyone, this doesn't have to be affiliated with the school at all, but if you know of anyone who may have some type of a tax problem that you haven't been able to resolve with the IRS, okay, there is a program called the Taxpayer Advocate Service that will assist practitioners in person at the upcoming Problem Solving Day. Sounds like a good name for a math day, doesn't it? And that is going to be here at Lawson State Community College, here on the Bessemer campus. Okay? It will be just next door here on the Millsouth building. That's sort of the whitish looking building that's just outside the loop that goes around the building. The building on the outside, the Millsouth building. Is that on the main level of the Millsouth building. It's a lower level, but go up to the main level, and it's in the one-stop center. Okay? This will be Tuesday, March the 31st. That's the Tuesday after we get back from spring break. It will be from 9 in the morning until 2 in the afternoon. Open to anybody. So if you know friends, family members, people you know from church, people you know from the community, neighbors, anybody who might need some help with taxes, this is the place to go. And there's 2 names and numbers you can contact, Ms. Brenda Thomas, and I don't know if this is Dr. Dorothy Henry or Miss Dorothy Henry. We have a Dr. Henry that works here at the college, but maybe I don't know her first name. But anyway, it's Dorothy Henry. Both of them are 9293 numbers, and those are usually here on this campus. So I'm guessing they're both at the Millsouth building. Dr. Henry, she may be upstairs. Okay. The Taxpayer Advocate Service will be available to assist taxpayers with tax problems they've been unable to resolve on their own with the IRS. Our goal is to provide personalized, step-by-step guidance. If your tax problem meets our criteria, we will assign a case advocate to work directly with you. Okay? Now, there are multiple organizations that are participating in this. One of them is the Alabama Asset Building Coalition, AABC, that supports the IRS's, Internal Revenue Services, VITA, too many initials here, that's Volunteer Income Tax Assistance, and TCE, which is Tax Counseling for the Elderly. So this includes elderly people that might need some help just because they're getting, it may be, the tax forms have changed a lot. So even if they did their taxes all their lives and it was beginning to be a struggle, it's probably even a worse struggle now. So let them know about it, okay? Programs. The AABC will be available to help taxpayers file their 2018 and 2019 state and federal income tax forms. So there's 2 things happening at once. Taxpayer assistance for people who are having difficulty with the IRS and people who either need to file last year's or this year's federal income tax. Some conditions apply, and you can find them at AABC's website. The Taxpayer Advocate Service is an independent organization within the Internal Revenue Service. They're within it, but they're independent from it. So you're, by sharing information with them, not going to get you into problems. You know that they are independent. The TAS helps the taxpayers resolve problems, recommend changes to prevent future tax problems, and it protects the taxpayers' rights. Their services are absolutely free. So all this is being offered that Tuesday after spring break is free. experiencing a financial hardship or having a financial difficulties because of a tax problem, you're trying but haven't been able to resolve an IRS tax problem, or you believe an IRS system or procedure isn't working the way it's supposed to, come and learn more about it. It's a great service, a great program. Get the word out, get the people here who need to participate. All this information will be up here, the website. There's actually a QR code here, so get that. Now, the other thing you've heard several times before, but I'll repeat it again. It's probably running out of time. I don't know for sure, but the midterm progress report, the midterm student course evaluation for mini-term 1 courses does, I said that back. The mini-term 1 student course evaluations, they were late opening them, so I don't know if everybody got a chance to do them. If you were in the first mini-term course, or you know someone that was in one, please let them know those are open. Please get them done before they close things down. Then the second follow-up with this is that sometime soon they're going to be asking for midterm progress reports, which for this class, especially, one of my best classes ever, and I have received only half of you, maybe a little over half now, have turned in test 1. Only 2 have turned in research papers. 1 person turned in the second test already, and we're not quite through with the chapter yet, but evidently you were able to figure it out. So please get me some scores so I don't have to report something negative on the midterm progress report, if they ever remember to get around to opening. There is a faculty meeting this afternoon, which I wish I could go to because I have an awful lot of questions. And that's going to be one of them, but it's right in the middle of the mini-term class that I missed last Thursday because I was out of town. So I can't afford to miss another day with that. So anyway, I can't go to that meeting, but I have people asking questions for me. All right, any questions from you? All right, here's example 6. It's the top of page 332. We're in chapter 4, trigonometry. 4.8 is applications and models, and this is example 6, simple harmonic motion. It says, write an equation for the simple harmonic motion of the ball described on the preceding page. This was the picture of it, okay? And in that, they told you the period was 4 seconds, and you go from there. So the first thing they want to know is write an equation for the simple harmonic motion described here in this picture. And what would you say it was? Now, where is this one starting? At the equilibrium position, at 0. Neither up nor down. So evidently, you're going to be pinging it downward, okay? And when it goes down, it's going to go down to -10, and then it's going to go back up to +10. So you need to give me an equation for this simple harmonic motion. It's starting at equilibrium. Which trig function do you think that would be? Sine, exactly. Okay, so we'll write that down. Says write an equation and they said in the form, and let's go back one slide, they're writing their equations not as functions but as d equal, where d is the distance at any time t. So let me get my pen set up here. So that's going to be d is equal to a sine or cosine omega t, okay? Or d is equal to a cosine omega t, either one of those. And you said sine, so we'll go with sine. All right. Now, the next question was, what's your A? Anybody? If the amplitude is 0, you don't have much motion, do you? None at all. This is moving, so that's probably not this one. Okay? The magnitude of your amplitude is indeed 10 because that is an absolute value. And here is an kilo, right? Okay. All right. But which way is it moving initially? Down. So you would actually have your A would be negative 10. Okay? So we got the first part of that, and we decided to use a sign. So it would be minus 10 times the sine of, whoa, now what in the world is our omega here? Okay? This, we have to look at the wording here, where the period is 4 seconds. Okay? Now what does that tell you about omega? Omega here is what we used to call B. And how was B related to period? Does anyone remember? Say again? I can't hear you. No, okay. B has really nothing to do with it stopping. I'm asking, what does B have to do, what we used to call B, now call omega, what does that have to do with period? There is a relationship there. No one remembers that. How is your coefficient related to the period? Say that again. I can't hear you. Okay, I heard something cycle. A little louder.
The time for one complete cycle.
Oh, the time for one complete cycle. That's what a period is. But my question is, how is that related to our function, our equation? How is that related to B? We did this ad nauseum. You know, we'd start with, what is A? What is B? What does B tell you? You know? I used to know it so well. Okay, that's exactly what it is. How is it related to B or omega here? What is the relationship? Okay, that's what it's telling you. But what is the relationship between your omega here and the period? There is a mathematical relationship between omega, or what we used to call B, and the period. We did it every time we graphed the functions. And y'all were very good about answering it. But I guess last week someone shook the Etch-a-Sketch and erased all the... Never mind, y'all don't remember Etch-a-Sketch, do you? No one remembers what B, how B or omega is related to the period. Let me refer you back. It was so far back there. I think it's 4.2. No, 4.5. 4.5. Okay? On page 299, they start to talk about it, but they get to it on page 300. There it is. Anyone got a book? Sorry, maybe you should have gotten a book. Right, right. Anyone have a book? Top part of the page. In a little box. Yes. What is that? Period. Okay, your period is 2 pi over b, except our b is now omega. So the period is now equal to 2 pi over omega, because in simple harmonic motion, we're talking about omega rather than b. Same concept, okay? Now, we know the period. What we're looking for is omega. So can you rewrite that equation that solves it for omega? It's not that hard. Okay? In other words, omega is equal to 2 pi over the period. Now I'm going to put period as capital T. That's what we usually use for it. And this will be 2 pi over 4 because the period is 4 seconds. So what would that be? Pi halves. All right. So there is your omega. So minus 10, you could write the word centimeter in there if you wanted to, the units of pi halves t. There it is. Okay? An equation for this simple harmonic motion mentioned here. And that's it. Oh. It says note that the choice of A of either positive 10 or negative 10, but since they showed this going initially down, I put negative 10. I don't know why they put positive 10, but anyway they did. Okay? Now, a question they didn't ask, but I'm going to ask, is what's the frequency? Oh, they did ask it. They didn't ask it in the text, but they asked it here. I thought I had seen it somewhere here. What is the frequency of that harmonic motion? Anyone want to remember the definition of frequency? This I know we did last time as well. Is what? That is the definition of it. What's the formula or equation for it? Okay, you can do it that way, or 1 over the period. Okay, so frequency is equal to 1 over period, which would then be, if period is 2 pi over omega, this would be omega over 2 pi. Well, why go back through omega over 2 pi if all you have to do is do 1 over the frequency, 1 over the period, the frequency would be 1/4. Okay? You can go back and do pi halves divided by 2 pi if you want to. The pi's will go out and and then that would give you 1/2 divided by 2, which is 1/4. Yeah. So either way you do it, it's just so much easier to do 1 over the period. Okay? Because that's what it is. All right. Now, that was example 6. Any questions on that? There is a checkpoint coming up, and that's another application for writing a simple harmonic motion, and you can find the audio-video solution for that at larsonprecalculus.com. All right, let's see if there's example 7 listed. Oh, okay, let's see how they do it. Because the spring is at equilibrium, D is equal to 0. When T is equal to 0, the equation would be D is equal to A sine omega T. Y'all got that perfectly right because sine starts at the 0 position, at the equilibrium position. So what you have to do is find A and find omega. Okay? Because the maximum displacement for 0 is 10, and the period is 4, which you don't use here, you have the following. Amplitude is absolute value of A. That has to be 10, so you could use A is either plus 10 or minus 10. They didn't say that here. They're going to say it later. The period is 2 pi over omega, which was very difficult for us to find, which is 2 pi over omega equal 4. So if you solve for omega, you get omega is pi halves. Okay? Consequently, an equation for motion could be d is equal to 10 sine pi halves t. However, the motion they described, the way I understood it, it would have been a negative. It said, notice the choice of plus 10 or minus 10 depends on whether the ball moves initially up or down. They showed in the picture it moving down first, so I would have chosen minus 10. The frequency then is, and they did the same thing you said, go back and do by the formula omega over 2 pi, the more complicated formula, which would be pi halves divided by 2 pi, which comes out 1/4 cycles per second. So much easier to use the formula 1 over t, 1 over the period, and sure enough, that would be 1 over 4 cycles per second, where the period is how many seconds it takes to do one cycle. The frequency is how many cycles occur in 1 second. Okay. Now, I thought this was part of the checkpoint. Sorry about this. This is part, I guess, of example 7, maybe. I don't know. Or maybe this is just an illustration. One illustration of a relationship between sine waves and harmonic motion is the wave motion that results when a stone is dropped into a calm pool of water. Okay? The waves move outward in roughly the shape of a sine or cosine wave. Okay? If you were to do a cross-section of this, you see that looks like it's starting at a max, going down to a min, up to a max, down to a min, up to a max, down to a min, up to a max, down to a min, up to a max. Now, problem here, they're getting slightly smaller as you go. Okay? That's because water has friction. Okay? Believe it or not, there is friction in water, and it's diminishing that. But it basically looks like a sine or a cosine curve. And if this one is indeed starting at a plus here, then that would be a plus the max. That would be a cosine curve. If you started out here and went in, you'd probably be starting at a sine curve. Okay, because it's almost an equilibrium out here. Okay. As an example, suppose you're fishing and your fishing bobber is attached so it does not move horizontally, only vertically. And somebody goes by on jet skis and makes your bobber go up and down like this, and you're really upset with that because you think it's scaring off the fish. But as the waves move outward from the drop stone, your fishing bobber just moves up and down in simple harmonic motion. Now, the y is what's happening. This really should be t here. Time, not x, okay? And your bobber, over time, it started equilibrium, there was calm water, and then you drop the stone in, and it went up and down and up and down. This is really just doing this, up and down and up and down. But when you do time as the axis here, that spreads it out like this. A little bit later, it'll be doing like this. And then a little bit later like this. But they're always sine or cosine curves. Okay, this would be a sine curve to begin with. It goes to a minus cosine by the time it gets down there. Okay. That's the last slide they showed. They skip example 7. Let's us go back and see if we can do example 7. Consider an equation for simple harmonic motion. D is equal to 6 cosine of 3/4 pi times t. Find A, the maximum displacement. All right. Here's Aaron, right? So, what's the maximum displacement? Anyone want to make a guess? Okay. Are you looking at my writing here? Or did you get a 10? Huh? I'm sorry? Is that up there? No, that was the previous problem. This one right here. And you said a positive 10. Where did you get a 10? That one up there? This one right here. Where do you get a 10 out of that problem? The image. Oh, okay. Okay. Now, this is our problem now, not the other one. This is the problem. What's the maximum displacement? Anybody? Second? 6. That's your amplitude. Maximum displacement. That's the definition of amplitude. Maximum displacement. That would be 6 units. Now, we don't know. They don't tell us what the units are measured in. Centimeters, miles, whatever. I don't know. Okay? But the maximum displacement would be 6. Okay, the B question said, what's the frequency? Okay, what is the frequency? Okay, give me the formula you're using for that. Okay, okay, where this is omega, is that right? Okay, so frequency would equal to 2 pi over omega. Okay, so this would be 2 pi over, I'm going to write 0.75 pi, just because that's going to be easier to do the math with. Okay, notice here the pi's cancel out. That's too bad. I like pi. Okay, and 2 divided by 3/4. Now I think I'll write that back in. 2 divided by 3/4, which is the same as 2 times 4/3. That would be 8/3. And that would be cycles per second or hertz. Okay? Wait. You gave me the wrong formula, didn't you? Frequency is omega over 2 pi, isn't it? Yeah. I thought that looked wrong. Okay. I should know better than listen to you. Okay, no. Okay. That's what that is. Okay. Frequency is omega over 2 pi. Now, actually, how I would do this is this way. I would say omega is equal to, this is your omega, and this is, get your period first, t is equal to 2 pi over omega, which would be 2 pi over 3/4 pi, which is exactly what you were doing, 3 pi over 4, which the pi's go out, and that would be t is equal to 8/3, exactly like we got, and that would be in seconds. Okay, and then frequency is 1 over period, so this would be 3/8 of a second, cycles per second. Okay, or seconds to the -1 or hertz. That's the unit, this is per second. Okay, so 3/8 of a cycle per second. I'm going to erase, some of this here so I have more room to write. Okay. So that, that's the B part. The C part says the value of D when t is equal to 4. I'm going to put C over here. We want D evaluated when t is equal to 4. Guess what you do there? What you do with Glade? T is equal to 4. What is D when t is equal to 4? Guess what you do? What do you do with Glade? Plug it in, plug it in. Okay, you never heard the commercial? Okay, never mind, okay. So you just put t equal 4 in this. So d is equal to 6 times the cosine of 3 pi over 4 times t equals 4. Okay? What does that give you? Hey, you don't need a calculator, I don't think. 4's go out, right? Okay. What's cosine of 3 pi? Now, you might need a calculator for that, but hopefully not. Let's think about cosine. Cosine starts up here. That's at 0. Go down here at pi halves. Down here at pi. Down here at 3/4 pi. Up here at 2 pi. One complete cycle. So here's half a cycle is here. Complete cycle is there. Another half cycle has you down here at what was your amplitude? 6. So it's down here at -6. Okay? So cosine of 3 pi is -1. So this would be -6. You'd be down at the second valley you hit. Okay? That's your C part. The D part. The least positive value for t for which d is equal to 0. Okay? So you want the d to be 0. So 0 is equal to 6 cosine 3/4 t. You want the smallest value of t that makes that true. How do we do that? Well, first thing I would do is divide both sides by 6. And that wipes out your 6, doesn't it? Okay? You're out of there. So what you got now is cosine of 3 pi 4 times t is equal to 0. And you want the smallest value for t that makes that equal 0. Well, when is cosine equal 0? I gave it away just a couple of minutes ago. Where is the first time that cosine is equal to 0? So what value is this? Starts at 1, and t is equal to 0. Goes to 0, t is equal to 0. When does it go back to 6 up here? How many, what is your period for cosine function? 2 pi. So halfway to there is 1 pi, and halfway there is what? Pi halves, of course. So when this thing right here is pi halves. So this is 0 when 3 pi over 4 is equal, t is equal to pi halves. That's when cosine is equal to 0. So solve this for t. How do you do that? Multiply by 4 over 3 pi. Multiply by the reciprocal. If you multiply over the reciprocal here, 4 over 3 pi. The pi's go out. 2 will go in the 4 twice, so you get 2/3. T is equal to 2/3 of a second. Not very long, but you get 2/3. Well, they don't say what your t is, but I'm guessing seconds. All right, let's see how the book did. They got 3/8 of a cycle per unit of time, so that would be per second. Next, they got a -6, exactly like we did. Next, we got, I'm sorry. First, they had maximum displacement was 6, got it. Frequency was 3/8 of a second, cycles per second. C was -6, and D was T is equal to 2/3, whatever that is. It may not be seconds, whatever it is, that's it. There is a checkpoint. Please do the checkpoint as soon as you can after class. Let's hit vocabulary on page 334. A blank measures the acute angle that a line of path or a line of sight makes with a fixed north-south line. What is that called? A blank measure the acute angle that a path or a line of sight makes with a fixed north-south line. Bearing. Okay, very good. Number 2, a point that moves on a coordinate plane is in simple blank blank when its distance d from the origin at time t is given by either d is equal to a sine omega t or d is equal to a cosine omega t. Simple blank blank. Harmonic motion, perfect. Number 3, the time for one complete cycle of a point in simple harmonic motion is its time is the symbol for it is capital T. Period, exactly, okay? The number of cycles in a given second of a point in simple harmonic motion is its blank. Frequency, exactly. Homework exercises here. Any of the odds 5 through 11, they're all at Calc Chat. 9's at Calc View. Any of the either 13 or 15, they're both at Calc Chat. 15's at Calc View. Any of the odds 17 through, and this is where they go on and on and on, I would say 17 through 29, they should all be at Calc Chat. Then 31 through, 43, they should all be at Calc Chat. You may want to do a couple of those because some of them are bearings and navigation, some of them are geometry. Do whatever seems best. Then for simple harmonic motion, do either 45 or 47. They both should be at Calc Chat. 49 should be at Calc Chat. 51 or 53 should be at Calc Chat. 55 or 57 should be at Calc Chat. 59 is a true false. It should be at Calc Chat. And that finishes the section, and that finishes the chapter. Okay? If you want to do a few more review exercises, now you've already been tested on the first half of the chapter, so the test that you currently have, all but one of you, if you've already turned it in, you could do any of the odds that starts on page 341, 63 to 67, 69, they all should be at Calc Chat, 71 or 73, 75, they should all be at Calc Chat, 77 or 79, 81 or 83, 85, and 87 or 89, and 91. They should all be at Calc Chat. And then any of the odds 93, either 93 or 95, they should both be at Calc Chat. 97 should be at Calc Chat. 99 is a writing exercise. It should be at Calc Chat or something helping you. Not actually 99 and 101 are both writing exercises, so you can look at those if you want to. Then the chapter test, I believe what we did in this chapter, in this half of the chapter, I believe starts around number 14. Now, I think that maybe all the answers are in the back of the book, but still only the odd numbers are at Calc Chat. So that would be beginning at 15, 17, or 19. So they sure don't have many from the second half of the chapter. No, I'm sorry. They actually start at 11. 11 or 13. And then 15, 17, and or 19. So yeah, about half of it. There is a little blur, excuse me. I think I told y'all before that I found out a doctor last Tuesday not this past Tuesday, the one before it when I missed class, that my hemoglobin, hematocrits, iron, red blood cells are all very, very low. So after a while, I've just run out of gas. So I'm sorry if I'm yawning. Not that I'm bored. It's just I don't have any energy. Okay. But there's a proof. They show some Pythagorean theorem. There's tons and tons of proofs of the Pythagorean theorem. This is one of them. And then there's a problem-solving exercise that you could do if you're really interested in it. And these exercises, the odd numbers for them, I think are also a Calc Chat. They don't say that at the top of the page, but I think that's true. All right, all that done. Now, all of you here have received the second test, right? Okay. And graph paper if you needed it, right? Okay. So, we're about ready to begin. Chapter 5. Okay. Actually, we're not too far off from where we need to be. If we hadn't lost that week, we would have been right on the money. But we are also out of time, aren't we? So I guess we'll be starting chapter 5 on Tuesday. If we hadn't lost that week, we would be right on schedule. But y'all said you didn't? Yes. I'm sorry? Yeah, I said it. We're out of time. Yeah. And so we'll be beginning next week in chapter 5, analytic trigonometry. Don't we end at 10:45? Oh, I'm sorry. Thank you. I'm sorry. I was thinking my last class. Okay. They ended at 45. So let's move on to chapter 5. Okay. 5.1. See, I told you, losing oxygen here. Absolutely exhausted. But it's also the end of the week, and also all week long I've been working on fall schedule, and it has been such a mess. Finally got it done last night. I stayed until probably pretty close to 8:30 or so. So I'm just running short of everything. All right, we'll go from current slide. So chapter 5, analytic trigonometry. 5.1, using fundamental identities. I've got a little hint for you. This is true in most things. When you see something once, especially in a textbook or somewhere, you think, yeah, that's probably pretty important. When you see it again, you think, they're sort of emphasizing this, aren't they? This must be important. When you see it like the third and fourth and fifth time, you know this is something that's important. And how many times have we seen the fundamental identities? We saw them with the unit circle. We saw them with right angle trig. We saw them with angles of any, or trig functions of any angle. We saw them over and over and over again. And guess what? We're going to see them here too. You need to recognize and write the fundamental trigonometric identities. We will then be using the fundamental trigonometric identities. Get the idea they're pretty important to evaluate trigonometric functions. Simplify trigonometric expressions and rewrite trigonometric expressions. They are used lots of different ways. Okay? So here's the introduction. We will learn how to use the fundamental identities, there they are again, to do the following. Evaluate trigonometric functions, simplify trigonometric expressions, develop additional trigonometric identities, and solve trigonometric equations. So you get the idea, they're pretty important. And if you didn't think so, here they are again, okay? How many times have we seen them? This time, rather than T's or X's or whatever we used before, X's and Y's, we're now using U, okay? Doesn't matter what you use. The reciprocal identity, sine is 1 over cosecant. That means cosecant is 1 over sine. Cosine is 1 over secant. Reciprocal is secant is 1 over cosine. Tangent is 1 over cotangent. Cotangent is 1 over tangent. I like to look at them this way: sine, cosine, tangent, cotangent, secant, cotangent. However you do it, they're all reciprocal of one another. Okay? Then the quotient identity. I've had some other texts that call these ratio identity. Either one works. Tangent is always sine over cosine. Use that a lot. And cotangent is cosine over sine. Because they're reciprocals of each other, those are just reciprocal there. Now, these you really use a lot. Pythagorean identities. Sine squared u plus cosine squared u is always and never deviating from being 1. Now, I think I showed you in some previous life that if you divide everything on this equation by cosine squared, sine squared over cosine squared is tangent squared. Cosine squared over cosine squared is 1, and 1 over cosine squared is secant squared. So tangent squared plus 1 is secant squared, or written slightly differently, 1 plus tangent squared is secant squared. This one comes right out of this one. Or, if we divide everything by sine squared, this becomes 1, that becomes cotangent squared, and this becomes cosecant squared. So 1 plus cotangent squared is cosecant. Okay. That's just the beginning. You can rearrange each of these equations several ways, like sine squared u is 1 minus cosine squared u. Just subtract cosine from both sides. Or subtract sine from both sides. Cosine squared u is 1 minus sine squared u. Yet to know them, they're important. You can rearrange this one a couple ways. Subtract 1 from both sides, you get tangent squared is equal to secant squared minus 1. That works. You can do 1 is equal to secant squared minus tangent squared. That's true, but it's not used very much. Okay? Same thing here. You could do 1 is equal to cosecant squared minus cotangent squared. It's true, but it's not used very much. Or cotangent squared u is cosecant squared u minus 1. So there's lots of different ways to write it. Then you can start taking square roots off them. If sine squared u is 1 minus cosine squared u, the sine of u is the square root of 1 minus cosine squared u. And you can just keep going on and on and on using these various forms of Pythagorean identity. The hint that you'll be using a lot when you see these other identities you're trying to simplify, if they have squares in them, think Pythagorean. If they don't have squares, see if you can use reciprocals or quotient or ratios. But if they have squares, think Pythagorean. Okay, now here are some cofunction identities that are true. You just don't use them that much, but they are important things to remember. The sine of the complement of u is the cosine of u. Because the difference in angle u and pi halves is its complement. Okay? So the sine of a complement of u is the cosine of u. The cosine of the complement of u is the sine of u. The tangent of the complement of u is cotangent u. The cotangent of the complement of u is tangent u. The secant of the complement of u is the cosecant of u. And the cosecant of the complement of u is secant u. That's what the co means there of the complementary angles. And then these are pretty important, and you'll use them when you need to. Remember that sine and, of course, cosecant and tangent and, of course, cotangent are both odd functions, meaning the sine of minus u is minus the sine of u. Same thing for cosecant, same thing for tangent, same thing for cotangent. Cosine and secant, those are the only two even functions. And that means that the cosine of minus u is just cosine u. They're the same. On either side of the y-axis, they're the same. The secant of minus u is the same as secant. Those are the even functions. The other four are odd functions. Okay. And then, as I said just a few minutes ago, the Pythagorean identities are sometimes useful in radical form where the sign is plus or minus. Now, I may have not have said the plus or minus part. The square root of 1 minus cosine squared u, and tangent is plus or minus square root secant squared u minus 1. Notice that you've rearranged the tangent secant equation, subtract the 1 from both sides, then take it as square root and plus or minus square root. The sign depends on the choice of u. If you know what u is, in other words, which quadrant u would be located, then you know which to take. Because sine is positive in which two quadrants? Second? And? First. Everything's positive in the first quadrant. Okay, tangent is positive in which two quadrants? First and third. So tangent would be negative in the? No. Second and fourth, the sign would be positive, negative in the second. The third and fourth. Yeah. Okay. So, we're going to start using some of the fundamental identities. Whoops. One common application for trigonometric identities is to use given values of trigonometric functions to evaluate other trigonometric functions. Now, we've done this some already. We're going to continue doing it. So here's, I must be going to have company. My nose is itching like crazy. Okay. All right. Use the values secant u is equal to minus 3/2, and the fact that tangent u is greater than 0, in other words, is positive, to find the values of all 6 trigonometric functions. Okay? Now, I guess the first question I would like to ask you is, what is your, now this is going back to not necessarily your unit circle, but most of the other renditions we had of the fundamental identities. What was your definition for secant? No, it almost never was. In that formulation you're talking about, by the way, I meant to erase this yesterday and I didn't. I'm glad no one came in this morning and thought they were going to be 38. This is because I was working on this fall schedule. I hated that class. But I had to because they said it absolutely had to be in yesterday. And summer schedule had to be in Friday. So they gave us 3 whole days to work on fall schedule, which is the most complicated schedule of the whole year. And for me, it really was. Okay. Now, in terms of x, y, and z, since you gave me an answer in y, let me get my pen set up. Okay. Now, I'm not going to do a unit circle. I'm going to do just some old circle. Not necessarily a unit circle. In fact, not necessarily a circle at all, but okay, if you just imagine it might be. Now, y is the distance up and down the vertical axis. X is the distance right or left of on the horizontal axis. And r is your radius anywhere. Okay? Now, in terms of x, y, and r, what is a secant? And if you don't know that, it's okay. But what's the reciprocal of secant? just had it in the table. You just answered that. What's reciprocal of secant? Cosine. Okay. Now tell me what cosine is. Thank you. Okay. If it's reciprocal, yeah. But I mean in terms of x, y, and r. What is cosine? Okay. It certainly has to do with x. And back when we were dealing with the unit circle, it was x. But we're not in the unit circle anymore. We're x, y, and r. So what is it in terms of x, y, and r? X is involved. Do you remember caught another hen?
What you ask?
Cosine.
Adjacent over.
Exactly. Now, what's your adjacent in our letters x, y, and r? X. This is your x. So cosine, I'll put u, is equal to x over, and what's your hypotenuse in x, y, and r? That's the r. Got it. Now, what did you tell me cosine was? Okay. So secant then would be the reciprocal of cosine, which would be r over x. Okay, we're getting there. Okay, now I want you to remember one special thing here. R is never negative. Remember, it's the square root of x squared plus y squared, right? Never negative. R is always positive. So then let's look at the secant up here. Secant u is equal to negative 3/2. Can you tell me how I should label my circle here in terms of that? What do you reckon the r is? If secant u is r over x, and we have up there that secant u is minus 3/2, what would be the r? 3, exactly. So this circle is not a unit circle, it's a 3 circle. 1, 2, 3. 1, 2, 3. 1, 2, 3. 1, 2, 3. I didn't get that bottom y very good, but something like that. Okay? What do you reckon the x would be? Really? Close, but not quite. Negative 2. You had to put the minus somewhere. It can't go with the 3 because r is never negative, so it has to go with the x. So here's your x. So if that's the case, you're either up here or you're down here because x is 2 and r is 3. So either one of those would work, right? Okay? Now, they also tell you that tangent u is positive. And I want you to tell me where tangent is positive. You've already told me that today, too. First and third quadrant. Well, you can't be in the first because this wouldn't be true in the first, so you've got to be down here. So this is where you are, folks. U is equal to this angle right there. Okay? Where r is 3 and x is equal to minus 2. Okay? Now, from that, you should be able to tell me what cosine is. It says find the values of the all six trigonometric functions. One of those is cosine. That's the easiest one. What would it be its value? Negative 2/3. Perfect. It's the reciprocal, right? We just said that. Minus 2/3. All right. That was the easy one. Okay? The rest of them we're going to have to do a little bit of work. Okay? Oh, boo, yes. Who wants to do any work, right? Okay. Now, what other piece of information are you going to need to get the other 4 trigonometric functions? By the way, what are they? Say again?
Are you asking what are the other trigonometric functions?
Yeah, other 4 trigonometric functions.
Sine.
Sine of u. Say again? Say again?
Cosecant.
We got cosine and secant.
Cosecant.
Okay, we got cosecant u, tangent u, and cotangent u. Now tell me what any one of those is in terms of x, y, and r. Say again? What is that? That was tangent, okay. And what's your opposite? Y over x, perfect, okay. Cotangent would be x over y, because it's reciprocal. How about sine? Is what? Y. Okay, that's if you were on a unit circle. Are we on a unit circle? Was it in terms of x, y, and r? Y was right for the first part. R, y over r. Okay, and what would cosecant be then? R over y. Got it. Okay. Now, what is it we need to know? We know x, we know r. What do we not know? Exactly. And we need a y in every one of those, don't we? Okay? So how are we going to get our y? Are we? Say again? Pythagorean theorem. And how does that go?
This is going to be y equals square root x squared plus
R squared
plus
minus x squared. Because x squared plus y squared is r squared. So you subtract to get the other one. Okay? So, we know both of those, don't we? So what would y be? The square root of? Nine minus, say again? 4, which is the square root of 5. Okay, now we got our other 4, don't we? What is sine? And by the way, wait. Which quadrant are we in, folks? And what is your, I can't find, there it is. What is your y in the third quadrant? Minus. We really should have written this as plus or minus the square root of r squared, which is plus or minus square root of 9 minus 4. But since you're in the third quadrant, your y is negative. So it has to be a negative root 5. Now we can write down what sine of u is. What is it? Okay, did you say square root of 5 over 3? You left off something.
Oh, plus or minus.
Minus, not plus or minus, minus. You know you're in the third quadrant, right? So it has to be minus, okay? Which one you want to do next? Cosecant. What is cosecant? Of u?
3 over negative 2 over 5.
Okay, I'll put the minus out front, square root of 5, okay? Now, sometimes they don't like that and they write it 3 root 3 over 5, 3 root 5 over 5, but in this case, I think they leave it, no, they do it both ways. So you could also write that as minus 3 root 5 over 5. If you rationalize the denominator by multiplying numerator and the denominator by square root of 5, okay? Either one of those answers is fine. All right, do tangent next. What tangent u equal? Minus root 5. Negative What you say, 2? Yep. And what's that? Minus over minuses? Yes, root 5 over 2. Time out. Does that make sense? Is the tangent positive in the third quadrant? Yes, it is. So yes, that makes perfect sense. If it came out negative, we got problems, Houston. Okay? All right. And what's cotangent? Yeah. Okay, if you wanted to. Over negative root 5. So that would be 2 over square root of 5. If you wanted to rationalize the denominator, that would be 2 root 5 over 5. Perfect. Perfect, perfect. Okay. Way to go. Please do the checkpoint. Seemed like we struggled enough with that and need to do the checkpoint. Okay? Well, let's see how they did it. All right, for me to erase? Hang on to what you... Okay, okay. Okay. If they give you something like this, my best suggestion, give it in terms of you can do it opposite, adjacent, and hypotenuse. You can do it X, Y, and R, whatever. I like X, Y, and R because that gives you the full circle, and because of opposite over, opposite and adjacent, you always think of those as acute angles. This gives you the whole circle. So X, Y, and R to me is the best way to go. Okay. And then usually they give you 2 pieces of information so you can nail it down. All right, so I'm going to erase what I've written and see how they start. Using a reciprocal identity, that was the easy one. The cosine u would be 1 over secant u, which would be 1 over negative 3/2, which is really a hard way to do it. Why didn't they just say it's reciprocal of secant u, which means negative 2/3. You just take the secant, flip it. Okay, keep the sign because of cosine is negative, secant's got to be negative. Okay. So that was the easy one. Okay. Next, you use the Pythagorean identity. You have that sine squared. Now, they did it slightly differently than we did. But you can certainly do this. I like to visualize. They like to use formulas. Okay? But sine squared u is 1 minus cosine squared. And we knew cosine squared u from here, or cosine u from here. Okay? So we're trying to get to sine u. Okay? So we start with cosine squared u is 1 minus cosine squared u. Then we take a square root, but that, ooh, goodness. Oh, okay. So they're just plugging in the value. Okay? And that gives you 1 minus a square root of, no, 1 minus negative 2/3 squared, which would be 1 minus, the minus inside gets squared away and becomes a plus. The minus on the outside stays a minus. So it's 1 minus 4/9, which would be 5/9. Okay? That's what sine squared is. Then you do, because secant is negative and tangent is positive, it follows by what we did. And see, if you had just done the X, Y, and R, all this comes out at the same time. Okay? They're doing it separately, and they're just having to remember secant is negative, tangent is positive, so you got to be in quadrant 3. I mean, it's true, but they didn't show why they did that. I mean, it's absolutely true. Okay? So, because sine is negative, when u is in quadrant 3, yes. Is it time? Then choose the negative root and do sine u is equal to minus root 5 over 3. Okay. And then knowing sine and cosine, you can get everything else. Because cosecant would be negative 3 root 5 over 5. Tangent or cosine you already know, and secant you already know. Okay? This, this drives me nuts. Is this right? If cosine is minus 2/3, they say the secant is that. No, it's not. They gave you in the original problem, the secant was minus 3/2. So this is totally wrong. Oh, I see what they did. This belongs down here, this belongs up there. Okay? I don't know how they got that screwed up like that. This belongs there, that belongs here. Then this follows from that. I didn't even pay attention to the first part there. Okay, so this is minus 3/2. Okay. This is, what's that? That is. This would be sine over cosine. If you did x, y, and r, that's even easier. Root 5 over 2, and this is 2 root 5 over 5. Okay, we'll begin with example 2 next time. You did get enough to do some homework exercises. I think you can do any of the odds, 7 through 11. They're all at Calc Chat, 7's at Calc View. Okay? We'll hold off and do the rest of them later. Okay? But you got plenty to work on. You got your second test. You got homework for the last section in chapter 4, and now you got a little bit in chapter 5. So it should be a fun weekend, right? Yeah, plenty of trig to work on. All right, we'll end this one.